I'm really happy today to be presenting some work that I hope will address an actual industry problem, unlike a lot of academic machine learning research. And the particular problem that motivated, in fact, all of this differential equations research I've been doing lately was a regularly sampled time series. So, most of the data sets we work with in academic machine learning don't actually have this problem that they look like some trace of activity of a person, like a user or a customer or a business or a patient over time. But these data sets are ubiquitous. So what I'm showing here is the times at which different measurements were made about a certain patient in an intensive care unit in a hospital. And you can see that, according to what the doctors were thinking, they measured all sorts of different quantities about their blood and, temperature and things like this. And this is also the case for, most business data. And I would say most of the nice new models that we have in deep learning don't really fit in this setting. So the standard things that people do when they're faced with this kind of data is, number one, is binning, where we divide our time up into equally spaced chunks, like every hour, and do something like average all of the data within each bin. But this gives you either some empty bins, or you're destroying information by averaging many different observations within a bin. And the other thing that people do is they say, okay, well, I'll impute. If I'm missing data, I'll just sort of put in some average or do some exponential decay. This is bad because it actually requires us to solve the original problem we were trying to solve, which is how do I predict what the data is going to be when I didn't observe it? And it permanently messes with the uncertainty in your model because the model just sees data and it doesn't know whether it's the real original data or some imputation. So I think there should be some sort of, statistician's Hippocratic oath that says, your first step of your procedure shouldn't be to mess with and throw away a whole bunch of data. So what I'm going to propose that we use to deal with this type of data is latent variable models, or latent variable time series models. And I'm not the only person working in this direction. And in particular, David Sontag recently spent a long time saying, hey, why don't we build a model that looks kind of like a Kalman filter, where there's some latent hidden state Z that describes the state, like the position of our missile or the state of our patient or whatever, that evolves nonlinearly through time with noise. And we get to see some noisy observations of those that depends on that latent state, such as a radar track or a doctor's note or a reading or something like that. We can write down these models pretty easily. We can use a neural network to specify the transition dynamics, and another one to specify the emission probabilities. And this defines a joint distribution over all of the hidden states over all time steps and all the observations at all time steps. The only remaining problem is how do we integrate out over all of the latent time steps? So it turns out, we can use Markov chain Monte Carlo, whatever we want. It turns out that it's useful to use another neural network, maybe some sort of recurrent neural network, to look at the data and consume it and output a distribution over Zs. So this is the general sort of variational autoencoder framework, where we have one model that's the generative model, and then here we have the recognition model that looks at the data and tells us how to approximately integrate out all the latents, and tells us, what do we think the hiddens are given the observations. One sort of point I want to stress is that if you wrote down the generative model, you've already sort of implicitly defined the answer to any query you might make about your model. This recognition network is just there to help you speed up integrating over Z. Okay, so we would like to use these types of models for a number of reasons, namely that they can handle missing observations totally naturally, but they've only been developed in discrete time settings. So how can we bring them to continuous time? That's what this talk is going to be about. So obviously, the set of tools that we're going to use for continuous time dynamics are ordinary differential equations. That's basically just the definition of how do we formalize continuous time dynamics. And to be specific, we're going to say that we have some vector-valued state, Z, that can change continuously through time. And that change is going to be specified by some function f. And every function or distribution in this talk can implicitly be defined by some neural network with 1 million parameters. And we're going to fit those with gradient descent. That's just sort of implicit here. Once we know the state at some initial time, we can now compute the state at any future time by just integrating f through this, along its trajectory. It might seem pretty hard to do this in general, so we rely on all these numerical approximations like Euler's method, which just says take start at the initial point, take a small step in the direction of the gradient field, and keep moving, taking steps according to the dynamics at the point that you evaluated. And this is obviously like a very primitive numerical solver. It accumulates error unboundedly, but nowadays we have, based on 50 years of great work in the numerics community, nice adaptive solvers that have sophisticated extrapolation strategies that can take very large steps. Okay, so how can we take advantage of ODEs and make some sort of continuous time model? So the obvious first thing you could do is say, RNNs are pretty good time series models, at least for making predictions in the future. Why don't we just replace the update equation with a ODE initial value problem? So the idea is that instead of defining a function that takes in the new x and updates the hidden state, we'll just say that we'll define a function that says, how does the hidden state evolve? Maybe as a function of the last x we saw or something like that. So this is, we call this like an ODE RNN. And it's kind of it's nice because now I can ask this RNN to predict at any time delta, not just one step at a time. And we also have to define two functions, one for how the hidden states evolve while you're waiting for new data, and then how to update your hidden state when you see new data. So we get to factor our model a little bit more. However, I'm going to argue that it's much better to use a proper latent variable model, even though we have this extra pain of having to integrate out the z's. And I'll give you some examples of why it's better later on. But anyway, so the continuous time version of a latent variable model just says that there's some initial z t0, and that's like the state of the patient when they're born or something, or the state of the business on the day it was founded or something. And then the dynamics of this state are deterministic as a function of that initial state. And now at each time that we have an observation, that observation probability only depends on the latent state at that time. So this is the graphical model where diamonds mean deterministic and circles mean random. And this is sort of the equations that you could write to sample data from this model. OK, so any questions about the setup so far? Yeah, so exactly. This is a huge, we assume the world is deterministic, and this is a huge assumption that we're going to chafe against later on. But it's the first step. If we only have ODEs, ODEs are deterministic. We haven't yet injected noise into the dynamics. OK. So we just have a paper at this upcoming NIPS that says, oh, OK, well, yeah, let's try to do inference in this model. And this is something that's kind of just an engineering detail, but the idea is on the right-hand side, that's the same model I had on the previous slide. And then we have to somehow build a network that's going to take in all the observations we saw and ask what do they say about the initial state. So this is a bit confusing, but I've mirrored time here and I'm saying that we'll use one of those ODE RNNs to consume all of the data that we saw and then output a posterior over the initial state of our system. So this is like, we look at all the patient's records and then ask, what does that tell us about what the patient's initial state was? And then if we want to make predictions, then we just run our dynamics forward from that initial state. Right? It's maybe a little bit of an awkward construction, but it is a way that we can do inference in this model. So one thing I want to say about recognition networks is, again, they're just a way to speed up doing inference. We actually could throw this away and replace it with some sort of gradient-based approximate inference or change the architecture. This is not like an important detail. It's just a hack to make things fast. This is what's the right-hand side is what's defining the actual model. OK, and again, this is just a variational autoencoder that we're building with a funny encoder that goes through time, standard fixed dimensional latent vector, and then another funny decoder that has an ODE inside of it. OK, I realize that I've had a lot in this first part of the talk. Feel free to breathe and ask any questions.
So you're assuming that the randomness is a Wiener process, right?
So there's no Wiener process yet. Right now, the Z is a fixed dimensional vector.
No, but sigma.
Sigma. Oh, the sigma. Oh, yeah. So here, that just means that we happen to define our approximate posterior over Z0 as a Gaussian with some mean and sigma. Well, I guess I would say Wiener process is defined through time, but here the only randomness is at a single time point, so it's just a standard finite dimensional Gaussian. But there will be Wiener processes in a minute. Any other questions?
Are you just making usual sums VAEs that this gives you correlations?
Yeah, so we're using the standard tricks for VAEs where we're saying we'll actually have a diagonal covariance Gaussian for the approximate posterior. But I mean, again, this is just an implementation detail. If we thought that the posterior wasn't expressive enough, we could replace this and do I-way or something like that. So, yeah. Yes?
Why do you mirror the time from the beginning or during the encoding phase?
Yeah, so why do we mirror time? Well, we have to somehow consume all the data across the entire time series and end up outputting something at time 0. So I think it makes sense to start at the end and go back towards time 0, because that's where we have to end up. I think there could be more exotic encoder architectures here, and this is just a thing that has the right type, and we can stick a bunch of parameters in. Yes?
So in the case where your variation is non-Gaussian, it's just something else, would that be accounted for in your sigma in this equation, or would it be an additional parameter in whatever equation?
You're saying if the approximate posterior needed to have more structure, how would we do that? So when you said the variation in the model, I didn't know which part you're talking about.
So if there's noise, but noise is occurring not evenly distributed.
Oh. So first of all, I want to say that the noise in the generative model only happens at the sampling the initial state and then at the observations. But this will in general lead to a totally non-Gaussian true posterior. But again, there's like a whole literature on how to build more and more sophisticated approximations to the true posterior. OK, well, I want to make sure I get to the SDE part, so I'm going to keep moving. OK, so to make this a bit concrete, here's us training this model on a toy example. So at the top, we have some different time series that are irregularly sampled, and they have one-dimensional observations. This is just so that we can view everything. This works in higher dimensions. And that f function, the dynamics function that I was talking about, so the latent state has dimension 4 in this example. So we can only show a 2-dimensional slice of it. But the idea is that, yeah, that's what the neural network in our model is parametrizing, is this function that maps from a 4-dimensional state to a 4-dimensional time derivative. Here we're showing just a 2-dimensional slice. And this model, as we train it, successfully learns that there's sort of like some sort of periodic dynamics going on in this model. Of course, we can learn all sorts of dynamics, not just periodic ones, but that's just the simplest ones that we can show in a small data set. And now having trained this f, and having an initial distribution over the z's, if I sample initial conditions and then run them forward according to these dynamics, I also see more periodic time series, just like I saw in the training set. OK, so moving on. So I was saying before that we should try to use latent variable models and not RNNs. And here is a setting where I sort of try to demonstrate that. So here we set up a true system that matches the assumptions of our model, which is that there's an initial random state in some physics engine, the Mujoku, and then we just run things forward without any control from that initial state. So everything actually is deterministic and continuous in time. And here we can look at, so what happens in these movies is that the guy starts in the middle of like the sky, and then he falls for a little while, hits his butt, and then just kind of sits there, and bounces and then sits there. And he hits the ground right between these two frames. And if we look at the norm of the dynamics in our latent ODE model after we fit it to this data, we can see that, oh, something happened right there. The dynamics, the state changed a lot in that time. So if I was looking at my model and it was like some complicated high-dimensional data, this sort of summary statistic of the state would be informative. Whereas if I just look at the change in the hidden units of an RNN, like there's an entire belief state being encoded implicitly in these vectors, but it's not encoded in any interpretable way. And so it's kind of like just looking at the sort of random hash of someone's brain activity to figure out what they're looking at. It's like you could reverse engineer it, but it's really hard. And so here we see that the change in hidden just looks like noise. OK, so we ran this model on that UCI data that we talked about. So one thing I want to say is all this stuff, we have code available. I'm going to talk about that. But it's hard to use, right? This is all like early days. It's pretty complicated. The first thing you should definitely try is taking an RNN and then also feeding it the delta t, the change in time between observations. That's like a reasonable baseline. It's very easy to code, very easy to set up. It has a bunch of philosophical problems with it. It's like not clear what the true definition of the model is, but it actually works OK. And then the ODE RNN, I think it's like the nicest factorization. It's still pretty simple to use. That works pretty well. And what works even better is our latent ODE, where we actually treat this as a latent variable model, even though the assumption is not quite right. One thing that didn't help on this data set, but I think will help in general, is this Poisson thing that I'm going to explain right now. So one thing that we throw away when we bin our data is that the time at which an observation was made can be very informative about the hidden state. So like if I tell you, oh, I didn't go to the doctor for 10 years, and now I'm going to the doctor a lot, without even knowing what the observations the doctor made or whatever, you would probably think, oh, I'm probably sicker than I was in those 10 years. Same with interactions with a customer. So anytime you try to write down any likelihood in this form for continuous time, you end up with this Poisson process likelihood, which just basically says you need to have a function that tells you how likely you are to see an observation given the state. And then to evaluate it, you need to compute this ODE, which is fine because we have ODEs in PyTorch now. So I think this is something that's like totally unexplored, which is conditioning on the times that observations were made for informing our latent states. And here we just show that we were able to model the observation times of different measurements in one patient in the ICU. And it like roughly matches, it made sense. OK, moving on. So yeah, code is available for all this ODE stuff. I won't say it's like completely plug and play. Like we tried. I think it's maybe worth a try. This stuff is slow. But it should be roadworthy at this point. Cross your fingers. So as someone in the audience rightly pointed out, this is a really weird model that says that we have deterministic dynamics, and it's basically saying that whatever happens to you in life was like fated in your stars from when you were born, and if you get hit by a car when you're 20, it's like that has to be somewhere in your latent state or your initial state. And so as we try to model more and more of some time series, we have to stick more and more stuff into this initial state. It's just a broken assumption, right? I initially started off by saying these deep Markov models are great because they add noise. Well, one of the nice things about them is that they allow there to be some noise at every state transition. So how are we going to add noise to our ODEs? Well, it turns out that if you add noise at every infinitesimal step, you end up with the stochastic differential equation, which is defined in a slightly roundabout way, where we say that the change in z is this deterministic part, that if we just stop there, we have an ODE, plus this sigma, which says what is the scale of the noise, times a change in Brownian motion, which is just a way to define a Gaussian noise. This is the exact same SDE formulation that people have been using for 70 years. And I'll just say, it's a good fit for any time there's a lot of tiny interactions that you don't get to keep track of that are affecting your state. OK. Because we don't have that much time today, I'm going to skip over the related work. But someone made this awesome meme where we wrote the neural ODEs paper, and then like 3 papers came out called neural SDEs. However, none of these papers worked out how to efficiently compute gradients through SDE paths, which is something that had already existed in ODEs for 50 years, and we just ported it to PyTorch. So I was really surprised when we started working on SDEs that there was no real reverse mode theory worked out for SDEs. So just to remind you very quickly, the reverse mode for an ODE can be solved by just solving another ODE backwards in time. I got to sort of skip over some of this stuff. And because we can compute ODEs, we can reconstruct the trajectory. This requires much less memory than even a standard like neural network. And all we have to do to run ODEs backwards in time is stick a few negative signs in front of the dynamics and the time. So most of what we've been working on lately is saying, yeah, let's just bring this whole thing over to SDEs. And one big problem is that it's hard to store all the noise. Like we have to sample an entire function somehow and use it on the forward pass and the reverse pass. This is like the reparameterization trick, except like infinite dimensional. And it turns out that you can do this with this really nice recursive construction of Brownian noise, where you can just keep sort of subdividing the interval and sampling conditioning on what you've sampled before. The other thing is that it turns out mathematically, it's like, I've been working with this probabilist, and he was like, what does it even mean to run an SDE backwards? Like, you got this like, forward filtration, and you're also going to like filter it backwards. But it turns out, and I was like, how can it not work, right? So I was the like sloppy machine learning cowboy, and he did everything carefully, but it turned out that our initial guess was right. You just slap some more negative signs, and everything works out. So now we have adjoint like backprop for SDEs. And amazingly, that didn't exist until like a few months ago. We set this up. It turns out, okay, and this is like a kind of subtle point, but so if we define some SDE with some F, that's like a neural network, and some sigma, that's a neural network, all I've defined is how to sample from my model. And this is kind of like the generator in a GAN. It's like, well, it's easy to write down a generator, but how do you compute likelihoods? How do you train it? And we initially thought, oh, we'll have to have some sort of like SDE GAN. It's going to be a huge pain in the ass. It turns out, though, you can actually compute a variational lower bound on the evidence by just integrating this thing that's sort of like the difference between your prior and posterior. So we define another SDE that gives us our approximate posterior, like that Gaussian we were talking about before, but now it's actually an entire random process that's non-Gaussian and non-factorized. Well, so the noise that we feed our SDE is a fixed Brownian process, but by having dynamics that get to depend on the state, we can have all sorts of non-Gaussian stuff.
Yeah, if you are varying your sigma.
Yes, exactly, and sigma does get.
Process, it is weakly stationary because it's a Brownian process.
Well, I agree that this Brownian process is stationary, but the transformed process, by running these dynamics forward, is certainly not stationary or Gaussian. But anyway, let's come back to that. Okay, well, anyway, so now we have this new alternative to like Gaussian processes, or this is like continuous time nonlinear state space models. And we just barely got this working a few weeks ago. Here's us fitting these approximate posterior to some irregularly sampled data with non-Gaussian observation noise. So we're using Laplace likelihoods. We could use any differentiable likelihood. And of course, it's not completely toy. Here's us fitting it to 50-dimensional motion capture time series data with a 6-dimensional latent space. And this works better than the other continuous time settings because we can A, add noise at every step, and B, fit tens of thousands of parameters, which before everyone else was just using forward mode, so they were fitting like 10 parameters. Okay, so this is limitations. I'll just summarize in saying it's slow. And there's some like technical questions about how to parameterize the noise. It has to be diagonal for everything to be fast, but a lot of stuff worked out really nicely, and the variational inference is like way easier to use than any sort of discriminator like GAN sort of setup. And yeah, in the future work, I think we can also use this to, if we define our process to be stationary, to actually skip over long time segments where there's no observations in closed form, because we'll mix back to the prior. And we're hoping to release the paper and code like this week. We'll see. Anyway, I want to say this couldn't have been done without Joychan Lee, who's a Google Brain resident, who's an undergrad, who actually learned SDEs just for this paper, coded everything up. He's amazing. Leonard Wong is a probabilist, and Ricky and Yulia, who are two students I've been working with. So thank you very much.
We do have time for a couple of questions. Please wait for the mic.
Yep.
Thank you. It's definitely interesting work. I'm curious if you think there's anything that can be done to have this work on larger latent spaces with higher dimensions.
So the question is, yeah, higher data dimensions. I mean, I think this already scales pretty well. Like, the observations can be however high dimensional you want. And then I think the latent space can be probably on the order of tens or hundreds of dimensions. Yeah.
So I guess I'll ask the crank question. Why haven't you made all your millions on the stock market with this yet, or what am I missing?
That's a good question. So I actually do. So the question is, if you're so smart, why aren't you rich? Why aren't you making big bucks in finance with this? So to be honest, I don't know that much about finance, except I know that they love SDEs, and I think finance people will like this a lot. I will say that for short, time scales, you can just discretize time. Okay, I guess the thing is that most finance time series that I know of actually have regularly sampled intervals. They still use SDEs to model them, but computationally there's no problem if you actually want to fit every minute that there's a stock, you model the price changing every minute. So this is much more appropriate for more real businesses where you have, it's your customer for a month and then suddenly you have 3 interactions with them, something like that.
Thank you so much again, David.